Welcome to Bienville Studios. My name is JT Nesbitt, and this is my love letter to William Henderson. This is my love letter to Ettore Bugatti. This is our very first test engine. This is not a running engine yet, but rather the heart of a full-scale concept vehicle that I'm building. Building a concept one-to-one in the real world is critically important for testing part fit, systems integration, and proportion in the real world, and critically important for testing ergonomics, which is something you just can't do on a computer screen. Keep in mind that I'm just a guy in a garage with a vision for the perfect American motorcycle. At first glance, this engine looks really big, but if you understand the packaging of it, what you realize is that we're actually 27 inches from the front of the engine to the swing arm pivot. Now that packaging is about an inch shorter than a Harley-Davidson twin cam, which is about 28.5. The Magnolia 4 also has the distinct advantage of locating the swing arm pivot in the correct position. Here, this high swing arm pivot allows an up angle on our swing arm of about 12 degrees, which is appropriate for the amount of torque that this engine is going to be making. The Magnolia 4 engine features a single overhead cam that's shaft driven. Behind this cover is a drive shaft that drives the cam. Our valves are arranged parallel to the bores and in line with the cylinders, very much like the Hispano Suiza V8 designed by Mark Burkett. This is a non-hemispherical combustion chamber. Like the Hispano Suiza and all of the Bugatti engines, this engine does not have a separate cylinder head. It's true monoblock construction, unified cylinder and head. And look at how narrow this engine is. It's only 9 inches wide at its widest point. Because of the way our valves are arranged, the valve size is actually restricted by the bore. Balancing valve head size and bore actually determines the length of this engine, because the valve head size determines bore spacing. Therefore, the overall length of this engine is actually determined by our intake and exhaust valves. The bore of our engine is 3.125 inches, the stroke 3.5. Our connecting rod center to center is 6.25 inches long. The bore of our engine is 3.125. The stroke is 3.5. This yields a displacement of 107 cubic inches, or about 1750 cc. Coupled with a long 6.25 inch center-to-center connecting rod, our rod ratio is 1.79, and our bore-to-stroke ratio is 0.9 to 1. This long stroke engine is all about generating torque at low RPM through high piston speed. Our crankshaft is a built-up crank. Just like the ubiquitous Japanese inline air-cooled 4-cylinders and all of Bugatti's crankshafts. The only difference is that our crank is machined in such a way to allow us to experiment with different configurations. We have the ability to alter traditional flat plane design and experiment with cross-plane design to yield more torque at lower RPM. The focus on low RPM gives us tremendous opportunities. Lower compression ratios and correspondingly lower combustion chamber temperatures. Pistons with long skirts that have tremendous stability in the bore and also transfer heat to the cylinder walls more efficiently. Lower compression ratios mean lower heat in the combustion chamber and also allow for lower octane fuels. Who knows what sort of fuels are going to be available in 100 years? Soft cam profiles with high lift and short duration, but super light valve springs, which cause much less wear on the cam. Shim over bucket, so much easier for valve adjustment. And because we're only spinning at half of what that system is set up for, serviceability and longevity are built in. A heavy and indestructible rotating assembly. All the things that give an engine a distinct American character. Overbuilt, understressed. This engine will last on generational timescales. The top end of the Magnolia 4 engine features the fewest number of moving parts possible to have a traditional 4-stroke internal combustion gasoline engine. However, the single overhead cam has some very interesting features. These are the access ports for valve adjustment, and we're using a shim over bucket lifted straight from the king of reliable air-cooled motorcycles, the Kawasaki KZ1000. Simple shim over bucket means way simpler valve adjustments because you don't have to remove the cam. Kawasaki KZ1000 shims are ubiquitous. Just about every bike shop has a set of Kawasaki shims. You'll notice the 4 separate ignition triggers for each cylinder located on the cam cover. This means that each cylinder has its own dedicated ignition trigger, and those ignition triggers are mechanically adjustable. That means that our ignition system can be modular and very simple. All the ignition system needs to do is recognize a signal from each individual piston and set the ignition curve. Because our triggers are adjustable, we don't need to program the VCU, since the triggers are already moving at half engine speed. Different advanced timing can be adjusted mechanically and for each individual cylinder to compensate for whatever fuel is available at the time, and they can be adjusted to help control heat. This eliminates a ton of programming and takes complexity out of our electronic system. Our fuel injection is about as basic as it gets. Simple, non-sequential port fuel injection with all the cylinders firing at the same time. This RPM-based system is only one step above mechanical injection. Having injectors fire at the backside of a closed valve turns out to be a really good idea. It helps to atomize the fuel, it cleans the backside of the valve, and it helps to cool the valves. A very simple ECU is all that's needed to power this system. This is the deletion of as many electronic systems as possible and replacing them with mechanical ones. The goal is to build an engine that is serviceable and will last forever. The Magnolia 4 doesn't use all the electronic bric-a-brac that motorcycles have acquired over the past 20 years. The goal is for a simple machine that's understandable, relatable, and that the rider can make a true connection with. As for computers, our traction control, lean angle sensors, adaptive aero, sport modes, and ABS are all housed here. You know, I've always had a disdain for transmissions that have more speeds than are absolutely necessary. And the rationale for carrying around transmission gears that aren't frequently used has always seemed like a shallow, cynical marketing exercise. How about fewer gears, less shifting, and a broader spread of torque generated by the engine itself? The transmission of the Magnolia 4 is a study in minimalism, a return to the traditional American 3-speed. Notice how narrow our transmission housing actually is. That means that the unsupported length of the shafts themselves, the counter shaft and the main shaft, are only 4.5 inches, with big, beefy, robust bearings on either side. The shorter the shafts, the stronger the transmission is. This transmission, like all the transmissions from the golden age of the American motorcycle, doesn't use a synchronizing shifter drum or shifter plate, and only has one fork. First and third gear are in constant mesh, whereas second gear is in sliding mesh. When you go from a 3-speed to a 4-speed, you don't add 1/4 more complexity, you add 5 times more complexity. And complexity is the enemy of reliability. The gears are thick, the shafts are robust, and the heavy-duty ball bearings are as close together as possible. You'll notice the super high location of the main shaft and output sprocket in relationship to the center line of the crankshaft. All of the heaviest parts of our engine are as low as possible. The center of gravity is low, but the swing arm up angle is still about 12 degrees. This is only possible with a vertically stacked transmission. The transmission countershaft is driven by the primary shaft, which has spiral bevel gears off the back of the engine. The primary shaft is supported from one end to the other with outboard bearings supporting the axial flux generator and starter motor all the way to the clutch side with a roller bearing in the clutch cover itself. The axial flux generator and starter motor combination eliminates all the complexities with a starter motor, the sprag clutches, the Bendix, solenoids, relays. It's now all in one housing. This is all thanks to modern 5-axis technology. Of course, this is the Kickstarter, which means that the Magnolia 4 doesn't have an absolute dependence on batteries. These are the compression releases used to aid in kicking over 107 cubic inch. Anybody who's kicked over a 4-cylinder knows that it's not the same thing as kicking over a V-twin. There are twice as many opportunities for ignition and 4 times as many opportunities for ignition over a single. Add port fuel injection to this formula and you've got an engine that's so easy to start. There's a certain romance with kickstarting a motorcycle in the act of turning biomechanical energy into a self-sustaining electrical, chemical, mechanical reaction. And it's also a statement of self-reliance. It's a great way to make a connection with your machine. And I certainly don't want the Kickstarter to be lost to time. The Magnolia 4 only has 2 fluids, oil and gasoline. Without the complexity of liquid cooling, we get rid of the water pump, the thermostat, the radiators, radiator hoses, and all of the corrosion that's associated with water-based coolants. But that means that we're asking our oil to do a lot. And to help our oil not just lubricate moving parts, but also aid in cooling our engine, special features are needed. Understanding how engine oil absorbs heat and disperses it is critically important. Engine oil is really good at absorbing heat, but not very good at getting rid of it. Optimally, hot engine oil should be splashed onto large surface areas and then transfer that heat. We have a lot of complex interior shapes with corresponding exterior cooling fins. This means that this engine could never be cast. It was designed from the very beginning to be carved from a solid billet of aluminum. There's a right way and a wrong way to design a cooling fin. And after reading Phil Irving's book and his chapter on cooling fins, I modeled all of these fins on his philosophy. That means a cooling fin with a generous root and a lot of taper. You'll notice that these cooling fins come to a very sharp point. Every time I see billet cylinder heads for a Harley with the flattened off fins, I realize that that's the wrong shape. Having a cooling fin with an extreme taper actually extracts heat. The depth of cooling fins is also really important, and you'll notice that our cooling fin depth in our head goes almost halfway through the engine. To maximize oil cooling, our engine is dry sump. And all dry sump engines actually have 2 oil pumps. Now, they may be in the same housing, but they're 2 separate circuits. For our engine, I actually broke the oil pumps up into 2 parts for packaging. An oil pump in the rear of the engine and for the feed, and an oil pump in the front for the return. This is main bearing priority oiling with secondary to the cam. There are underpiston oil jets as well. This is the main galley, which is controlled by this pressure relief valve. This knob tensions a spring to control oil pressure in the main galley. That main galley has its own dedicated oil pressure gauge. The underpiston oil jet has a knob in the front of the engine to control underpiston oiling and its own dedicated oil pressure gauge. This allows the rider to adjust oil pressure to compensate for ambient temperatures and to prevent over-oiling. All pressurized oil to the underpiston oil jets and the camshaft are controlled by individual jets. This allows us to put more or less oil into places that need more heat without over-oiling the entire system. While the oil from the engine sump is pressure-fed through this galley and used to lubricate the primary drive, the oil from the head is actually drained onto the top of the transmission. Now, these oil drains aren't randomly placed. They're placed to lubricate the transmission main shaft. The oil is allowed dwell time in the head to absorb heat before it drains onto the top of the transmission where it's splash cooled. You'll notice there are a lot of cooling fins on our transmission. The upper drains drain oil from the buckets, and if you think about it, the buckets moving up and down act like little pistons, creating vacuum and pressure, so they have their own dedicated circuit. The oil that dwells around the cylinder head, both the intake and exhaust, are drained here into the transmission with restrictors. That allows us to achieve optimal dwell time for this oil in the head to absorb heat. Oil is actually circulated from front to back through a series of veins into the central pickup. Having the oil tank located at the rear of the motorcycle and in cool air running underneath the machine allows lots of surface area for the tank to be able to disperse heat. The oil filter is a washable screen located at the pickup. No hunting around for the right spin-on oil filter in 100 years. The only way to access the oil filter is to remove the sump. This encourages the mechanic to clean out the sump at every oil change. The sump for the engine can also be accessed through a drain plug. A little squirt of mineral spirits and a little compressed air are all that's needed to clean out the engine as well. I'm a big fan of magnetic drain plugs, and you'll find them all over this engine. In fact, all the galleys can be accessed and cleaned through plugs. For reliability and serviceability, there are only 3 radial oil seals on this entire engine. One behind the axial flux generator starter motor, one behind the output sprocket on the main shaft, and one at the shifter fork. That's it. There are no gaskets on this engine. All the mating surfaces are designed with a little groove to allow for compression of RTV. Note how the intake and exhaust of this engine are actually really separate from the cylinder head itself. This is to allow airflow over both of those components, 360 degrees around the exhaust and the intake ports. All of these systems are designed with thermal management in mind, keeping our engine cool without the need for liquid cooling. The Magnolia 4 engine, my engine, is designed with longevity and simplicity in mind. This engine is designed to last for 100 years. In the 21st century, I can't think of any motorcycle engines that I would consider truly beautiful. And beauty is such an important part of my art. The way for me to express these mechanical ideas is to build a concept vehicle, a full-scale 1-to-1. Concept vehicles live on the edge of possibility, a delicate balance of reach and grasp. And unlike customized vehicles, they represent something far more interesting because we don't build them, they build us. And all great concept vehicles have one thing in common. They're the beginning of something, not the end.